two things up there while you were on break because I was working. One, how was AC produced? That's everything I covered on that PowerPoint slide, which is in Canvas under week 5 under the reading. I know, shocking. Should have put it somewhere you'd find it. And now we're going to cover waveforms. So we're talking about choking on my own whatever. Oscilloscopes and waveforms. And so this right here is a representative of a waveform. And this line right here we could say is the, huh? Oh, it's on freeze. Freeze. Freeze ray. Yes. I did one thing right. All right, so here's a waveform, and this line here could represent 0. It could, but you got to be careful because I could move it. I could, let's see, is it froze? Yeah, how about that? Well, that worked out well. There, vertical. I can move it up and down. And so if I move it up and down, and this is 0, well, that didn't work very well. So we're going to talk about that a little bit later. Get rid of this crap on here. There. So if I move that around, well, that's not really 0. But in between, in the middle of all of these would be the 0 line. You have the peaks and the valleys. And we'll come back around to that. So waveforms. There are many types. Yes, there are also buttons on the side of my pen to make my life miserable. All right. DC is straight. You just woke up or something a little. So DC. Are you okay? It's straight. That's not straight. You draw a straight line. All right. Then we could have something called chopped DC. Chopped DC. It's also called a square wave. Square wave. And that was where yeah, that one. Sawtooth, yep, that's another name.
You have an electric guitar, you use like fuzz pedal, that's what that's to like the sound wave. Not that anybody
And AC, which is called sinusoidal. Which went up and down. SINUS OIDAL. Ever watch medical shows? You have a normal sinus rhythm. There you go. Okay, B. Okay, back to this. One cycle of AC is from 0 volts to a maximum, to a max in one direction. Nothing to do with the band. Returns to 0 volts. Increases to a max in other direction. And returns to 0. Sort of. Now, that's one way to define it. But really, I would say one cycle is from one spot to a complete in the next spot. So if I go back to this, I'll come back. Don't freak out. Okay. So one of the things I do when I'm working with, and I expect you to do when because you'll be working with one of these machines, is you have to get your waveform balanced out. Like, let me see. It's kind of hard to do because I have to scroll down here. But you want to get it even. So like this would not help me because if this is my 0 line right here, I've got most of it down below and some of it up top, and that doesn't work. I want to get it right in the middle. So There we go. Yay. All right, so I would look at it, and it's kind of cheating, but get it right there. Okay, see how it's just touching this line here and just touching that. So I have 2 squares up, 2 squares down. And by the way, these lines have thicknesses to them, and you have to think about how you're reading it with the thickness. Some schools will teach you to read it right in the middle of the line. Fantastic. But you can't say, well, I'm going to read the top of the line, and then I'm going to read the bottom of the line. Then you're adding the thickness here. So if you're going to read the top of the line, read the top of the line here. It's top of the line, or bottom to bottom. Don't read top to bottom, because then you add the thickness of the line. And you can make these lines kind of thick on oscilloscope sometimes. So pick your spot and do it. So one wave would be, according to what I just wrote, 0, swing to a maximum, back to 0, swing to a negative, and back to 0. So this is one wave right here. Well, you could do that, but you could also move it back and forth and say one wave is from this peak to this peak. That's still one wave. It just starts here, goes down, up, there. It's repeating. So pick a spot wherever it starts repeating is also, you could measure a wave at that point. Yeah.
Well, will it always be like the same number on the top and on the bottom, like
Nope.
-5 and then or
Nope.
+5?
Nope. It'll be different frequencies. It can go back and forth. It can go up and down. So it can be different everything. Absolutely. And so with an oscilloscope, number one, you're going to set, just like you do on a voltmeter, how many divisions per volt you're going to get. Also how much this is time going across, and this is voltage or amperage going up. So you have time, but I don't want to get into reading the oscilloscope right at this point, because I don't have time for all that right now. So we'll come back to that. Okay. Let me see. So to help you out, I will draw a bad picture. When it really counts, I don't know. Okay. So do this here like this. All right, so this is 0 degrees. This is 90 degrees. And we're talking about the rotation of that armature. 0, 90. This is 180 degrees here. This right down here is 270. And then this is 360. One complete rotation of that armature that I showed you. So 0 degrees is at 0 volts. It's going to peak in the positive at 90 degrees. And then we're going to come back to 0. Oh, I'll keep consistency here. Oh, it's not consistent anyway. So we're back to 0 volts at 180 degrees. And then we are at the negative peak at 270 degrees. And then we are at 0 volts at 360 degrees, or back to 0. The number of these cycles per second, the number of these cycles per second negative peak at 270 degrees is the frequency. The number of these cycles per second is the frequency. So frequency is how many cycles, how many times from 0 back to 0, well, back to 360 returns per second is frequency. Also called hertz. Hertz. Talk about Hertz donut? Yeah. 1 Hertz is one cycle in 1 second. So if it took an entire second for it to do that, we would have 1 Hertz. Standard U.S. house electricity.
Man, you are blowing through this today.
Sorry.
Oh,
Got a long way to go.
I know.
Is 60 Hertz, HZ, which means we have how many cycles in 1 second?
60.
All right, you guys are really picking it up. So 1 cycle is 1/60th of a second. Common aircraft, AC, is 400 Hertz. And it can range from 360 to 800 Hertz. You doing all right, Eric?
I'm keeping up.
All right. 1 cycle.
I appreciate you checking in.
1 cycle may also be referred to as a wavelength. So 1 wavelength, 1 cycle. 1 cycle may be referred to as a wavelength. It's a wavelength. All right, we're doing okay? Amplitude didn't my friend Vector talk about amplitude? A vector is both direction and amplitude. Amplitude is the peak value. So if I'm measuring AC using an oscilloscope and I can see where it goes all the way to the top, I would measure it. You'll learn how to do that. Counting up little squares, centered out, count the squares, and say amplitude, how far it goes up. It's going to go up one way and have the amplitude going the other way too. So you have amplitude as the peak value, while we also have something else called peak to peak. Peak to peak is the value of peak times 2. So what's the electricity coming out the wall here in the house? Well, we have 60 Hertz is correct. What is the output in volts? 110. Why do they call it 120 a lot? So it's also 120 volts. So what we'll say 120, 110, 120. 120 volts. So we have 120 volts coming out of the wall, or 110. Is that a peak value or a peak to peak value? So if that were the case, then it would look like this. Well, is it from here to here is 110? Or is it from here to here is 110, and each one is 55 up and 55 down? It's going to be 110 up and 110 down. Okay, so that's 120 volts peak. And so how much is it peak to peak? So we can abbreviate P2P equals 240. We don't talk about that. If we got 240, then that's a whole different thing. So that stuff coming out of the wall, that's not 240, is it? No, it's 110. And also, it's not peak to peak. It's not even peak. We'll talk about that in a minute. But it's closer to that than it is peak to peak. So you don't double it. Don't double your electricity because it went from 0 to a maximum of what? 110. Went 0, maximum of 110. Then it goes back to 0. Then it goes to negative 110, just the other direction. Don't add them up. Right? It's just 110. It's 110 positive, then 110 negative. Positive, negative, positive, negative. Back and forth all day long. Damn near 60 times every single second. Why are you giving me a stink eye?
I'm not quite understanding.
Is it 110 or 120?
Harry?
Well, I'd say RMS, but that's.
No, I'll get there in a minute. I'll get there in a minute. I don't want to hurt them just yet. What do they say the standard house is? Because I've heard it both ways, 110. Some people say 120.
Yeah,
I don't know. Yeah, I've heard it both ways. Just don't fixate on that.
You used both numbers, so we're just, that's the second.
Oh, because he wanted to. So we'll call this 120 then. 120.
Okay.
So 120, then that would make this 60. 60 and 60. So it's not. It's not that. It's not 60 and 60. It's 120 up and 120 down.
Okay.
And the peak to peak then is 240.
Is there any question then?
But we don't.
Okay.
We don't talk peak to peak in this kind of stuff. Now, if you want to talk peak to peak, you say that. You say the peak to peak is. Otherwise, if you say it's 120, just go, okay, it's 120. That's what he said. Let's see. Oh, I'm way down here. Okay. Amplitude. I'll just put this in my notes. I don't ever use this particular term, so, but God help me if it was on the test or something, which I don't think it is. Alternation is 1/2 of a wavelength. Or cycle. And this is a little out of place right here, but it's, I believe it's a Q&A or something. The component being installed, that is in an aircraft or anything really, being installed must be rated for the frequency used. All right, phase. We're going to talk a lot about phase, and it's kind of important, well, everything's important, but that you understand phase as we go here. It is the angular difference between 2 points on an AC waveform. So in other words, if I have something that looks like this, what is the angular spot of this right here? 0. And what is the angular spot of this one?
360.
We'll call it 360. And this would be 180. This is 90. Okay, we're going to, might as well finish it. We're going to talk about voltages and amperages. And in theory, Now I'm just drawing this waveform. You could really be saying, well, is that an amp waveform or is that your voltage waveform? And I would say, yes, it just is. But in this case, I'm going to say, well, this black line can be volts, and then this blue line, blue, could be volts. This would be amps. And in theory, because the voltage is usually lower than the amps, right? The amps would look just like that. So if I'm measuring it, just like you would with the Simpson meter, anything else, you take your oscilloscope, you set it for voltage, you put it, this will shock you, you put it in parallel across something, you're going to get the voltage. Now we get the voltage. And then to get the amperage, you're going to have to do it in series. You break apart well, you don't always have to. Now, a lot of you, what you may want to try is try it a couple of times. Try it to measure amperage. I recommend you put it in parallel across something, watch the meter go to crap, then swap the two leads, watch it go to crap, then take them off, then break the circuit, then put it on, and then watch it, and then switch them one more time. Best method out there. So, okay. So, but you break it, now I'm measuring amperage, and I would see that this amperage looks similar to that, okay? But it's not always going to do that. It could look like this. Where it's starting out right here, we're starting out at 90 and it's peaking at 180. So when I say the angular difference between 2 points on an AC waveform, I'm talking about between here and here. What is the angular difference between those 2 points? 90 degrees. So I would say this circuit is out of phase by 90 degrees. And that's a bad thing. It's an inefficient circuit. I'll show you that later. Right now you're just working on the angular difference between 2 points on an AC waveform. So now you know when I say it's out of phase by 1 degree, 2 degrees, it means one of them is shift over, and it's off by that much, where it shouldn't be.
Will we get into how to fix that?
Yeah, just add a capacitor or a coil. It's just that simple. It's so simple. Can I move?
Yes.
Good, because I just did. Okay, point B. This is a bit of a, we already said this. There is such a thing called a polyphase. Polyphase. So some circuits use multiple phases. Here, like 3-phase. Oops. Like 3-phase. And I drew that little picture for you. I could do it again. So 3-phase AC is 120 degrees apart. I wrote actually here on peaks, but it's not on peaks, it's everything. The whole thing is 120 degrees apart. So 90, 180, 120. So it'll look similar to that, but I'm not continuing the waveform. So I'm just going to keep continuing. Then you'd have phase 1 comes in, phase 2, phase 3, and just goes on and on like that. And you have more power pulses per second that way. All right. C, voltage slash amperage phase. Now I think I just talked about that one, but we'll talk about a little bit more. So in an AC circuit, it is possible for the peak voltage to happen at a different time than peak amperage. So in an AC circuit, it's possible for the peak voltage, it should be AC, for the peak voltage to happen at a different time than peak amperage. Than peak amperage. If that does, it is called an out of phase circuit. This is an out of phase circuit. That's not a good thing. It's inefficient. And here to help us remember this is my good friend Eli the Iceman. To help us remember, ask Eli, E-L-I, the I-C-E man.
Say ask.
Ask, A-S-K. Don't get hung up on the wrong word. To help us remember, ask Eli the Iceman. So Eli, E. Is everybody hung up on the ask word there? Really? Okay. E-L-I. Best I can. Eli the Iceman. So in Eli, inductance. Inductance, which is a fancy word for a coil, is represented by, I have to scroll, by L. L is inductance. So inductance is represented by an L. What? I'm good. I'm good just talking.
Yeah.
Okay. I don't need the pen anymore. Okay.
No, you just use, no.
I was
that's-
surprised.
You just
L
say-
right. Instead of
Why is the L, do we start with the L?
Why do we start with the L?
Why don't we start with E? Like,
Why do we start with E? Let me ask you. Good question.
voltage.
What does E stand for?
Voltage.
Voltage. What does I stand for?
Current.
Look at you guys, man. Bunch of geniuses in here. You already knew all this. So in an, I know. There's somebody there. Whoa, slow down. E is what? Why did we not talk about this? You should have said something a long time ago. Well, now suddenly everything makes sense. Okay, so
Who's on?
yeah, what the hell's the R then? So in an inductive, inductance is the word for inductance and inductive, same thing. In an inductive circuit, meaning a circuit with a lot of coils in it, more coils than capacitors. In an inductive circuit, E, because it comes first, leads I. So if I have a circuit that has just resistors, it's a resistive circuit, and there's no coils in it, everything will be in phase. It'll look nice. It's hard to do. All the way down, all the way up. Volts and amps follow each other. But I add a whole bunch of coils to a circuit, and suddenly it is going to go out of phase. The voltage and the amps are now going to be following each other. What is going to happen? The voltage is going to lead the amperage. So you're going to get a bunch of volts, and then the amperage is, what are we doing? Oh, time to go? Okay. Now volts is already peaking and starting to come down. Here comes amps. What? Oh, we're peaking now. Okay. And so volts has already dropped off to 0, and here comes amps going, I'm at the top now. So not good, right? So voltage is going to lead, and whatever it's doing, amps are going to be following along. So not so good. So Eli.
When
like you can get a lot more amps without having as much.
Okay,
by itself.
yeah, good thing. The hard part to that explanation is starting at 0. Okay, it doesn't work if you kind of start at 0, you go, what? You almost take it from in the middle of the circuit and you're like, okay, voltage is already going, here comes amps. Otherwise, you just kind of start from 0. But if you want to start from 0, we're going to kind of do that where you have this sudden rush of voltage and you see it. And then the current kind of goes. And so, but anyway, we'll get there. So Eli, just remember Eli, L is the inductive, Eli, so voltage is going to lead the current. The current is going to lag. You have to say it both ways. Current will lag, voltage will lead. So that leaves the Iceman, or the ice part. I-C-E. What does the I stand for? What?
The Iceman.
I stands for? Current. E stands for? Voltage. All right. So capacitance is represented by C. Capacitance means a capacitor. We'll talk about these in much greater detail. So in a capacitive circuit, I leads E. Amps go taking off. And they do that because a capacitor is something that stores electricity. And really what it is, it's just like imagine a wire coming in this gigantic plate. And there's room for all these electrons. And then there's another plate over here. And so for a minute there, it looks like the circuit goes and it does something. So all these little electrons see that, and the minute the voltage starts just a little bit, they're like, I see a clear path, everybody follow me. And all the amps just go running, and they get to this capacitor, and they start filling up the capacitor, and then here comes the voltage. You're going to push them along. And the amps already got there because they saw this quick shortcut, and they all ran over there. Well, by the time they all realize that there's nowhere to go because you can't jump this plate, the voltage starts to turn around the other way, but then they see it and start going that way. So I'll talk more about that. That didn't make too much sense. But capacitors are really easy. They see, it's not an open, but it's just a clear path for electrons to go. So they shoot off and want to fill up these capacitors before there's any voltage whatsoever built up. So, and let's see, a circuit that is out of phase, that is the volts and amps aren't in phase, volts and amps is less efficient, All right, I already said this. Phase represented in degrees is called phase angle. Did I say that? I'll say it again. Phase is represented in degrees, called phase angle. All right, and that brings us to power. So let's talk about effective power. Effective power. You guys doing all right? This is a lot, huh? This is a very intense week. We're going to be doing a lot of maths, learning a lot of new stuff. But it's good, you know. This is generally speaking not a test that a lot of people do badly on, mostly because you're very focused. And it's not difficult stuff to learn. It's just new. Effective power. So when measuring DC, the effective power is the same as your measured values. Effective power is the same as measured. I could say our calculated values. It's just, it is what you see. It is what you measure. There's nothing tricky about it. That's why we never talked about it. It's, you know, E times I, you get your watch, you get your power, boom, done. That's just it. All right. It's not the same way with AC, because with DC, you have the same thing going. You have that voltage always moving. You have the amperage always moving. If you measure it on an oscilloscope, as long as the battery didn't die, you're going to see a line on an oscilloscope represent voltage that just goes straight forever. And you're going to see a line that represents the amperage on the oscilloscope just going straight forever. And so there is no difference. It just is, right? But in AC, you have to think about it. These lights are 60 times, well, it's actually more than that, but we'll just say 60 times per second. Is it actually double that? Yeah, it'd be double that, so that would be what, 120 times per second? They're off. So it's like, well, wait a minute. So it's only, you know, so it's, and then it's off, but then it's building up. So it only peaks out and reaches its peak so many times per second. So how do you figure that out? Well, the averages are different. Everything is different, right? It just isn't this one number. It's kind of like when you're trying to figure out how to measure the capacity of your battery after I came along and said, well, let's undo this, let's do that. Now how many amps are going on there? Like, come on, Kevin, keep it the same. Well, there you go. It's like I got involved or something. So in AC, the maximum, maximum measured value, VALUE value, only happens twice per cycle. Once up and once down. Twice per cycle. Let me see. Therefore, you got to come up with an average. An average value must be obtained. Well, you got to kind of be careful how you would come up with this average. So if I said, hey, let's come up with an average of this, and we have, you know, one cycle here. All right, so let's come up with an average. So okay, so let's plot this point, this point, this point, this point, and we just plot, we'll say 20, 30 points around this way, and we get a value. Then we do all this here. Well, what is the average going to be of those two?
0.
0. Why?
Because it goes up and down.
Goes up and down. So we have an average of 0, so they cancel each other out, so the lights don't work. Well, we know that's not true. So we can't do that. That's not right. So we got to do something else. Right. What do we do? Well, some guy or gal who was very smart figured out that the effective value of AC is that which produces, this is going to be right up some of your alley. Tobias, this is for you today. He was just working on this, which produces the same heat value. Heat value as in DC. So in other words, they basically took a Simpson meter and hooked it across a battery and figured out how hot those leads would get. And they did the same thing by plugging it into the wall and said, well, this equals that. They're just as hot. You know, so, right? So you just take a resistor or something and you figure it out. So they came up with this and said, well, wait a minute. If it takes this many volts for DC to do this and this many volts for AC to do that, that becomes our effective value. What was that about? Okay. Why does this feel like it just went to something else? So we've got, let's see. All right, so in AC, the formula for power is, you ready for this? Power equals I times E. Now, if we would have studied the Ohm's law wheel, which I really didn't make you do, it also gives you all of these. It is I squared times R, or E squared divided by R. So there's this squaring action that happens. So I shouldn't write this. You're just going to go, what the hell just happened? Freak you out. But I will tell you. Therefore, the heat produced is proportional to the square of the second. Sorry, proportional to the square of the current. It's proportional to the square of the current, this second one right here. So it has to do with squaring. So to figure out the average AC power, you average all of the squared values of everything. So take everything and square it. Well, now what happens if I square a negative number? Get a positive. So I got positives all the way up, positives all the way down. So you get an average of the squared values. Then you unsquare them, which is the square root. Okay, follow me? I don't want to write it down because then you'll freak out on it and think, oh, it's on the, so now you know it's not on the test. Okay, squaring all the values makes them positive. So it's different than just an average. Boy, and I decided one day I was going to go into this and do the whole thing and show you how that happens. So, so we'll just skip down to this. Another way of saying this is all the instantaneous values of the sine wave are squared. The results are added together, divided by the number of results to get an average or a mean. Mean means average value. So the square root of this gives the effective voltage. This is called the root mean square value. This is called the root mean square value. Root mean squared, root mean square is RMS. RMS, the root mean square value. So what does this mean? Well, it means something very important to you. So we'll make this point 2, and I'm glad I skipped all that other stuff. So hopefully you understand that it's just called the root mean square value. So when I'm talking about the value or the effect, the power, I'm talking about the current. Let's go back a little bit. We had the sine wave. We had the what? The peak. Then we had the. Now we've got root mean square, the RMS value. It is neither the peak nor the peak to peak. It is the effective value. It's what it's similar to DC coming out of the wall. So in other words, if we now look at this, now I could tell you that coming out of the wall, we'll say 120, the 120 volts coming out is what? The RMS value, which means that the peak must be more. So there's formulas for this. So, by the way, this is one of those weeks where, okay, so when we get to Friday's test, there's going to be a lot of this stuff on there, you know, calculating RMS and stuff like that. This is the week where, especially this week, we're going to have all kinds of formulas up on the screen for you on the test. I am not a big guy into, hey, you got to remember this formula. You have to know how to work a formula to be an aircraft mechanic. You don't need to memorize it. Since this is not practical actually, well, that's just, I was going to put, since it's not practical to actually measure all of the square roots and divide, we just use a formula. So we'll just put use the formula, then save time in C world. So E effective, EFF, so it's E effective equals 0.707 times the E max. So in other words, whatever that max voltage is, that peak voltage, multiplied by 707, boom, there you go. There's your RMS value. I could do the same thing. So it's I effective equals 0.707 times the I max, so whatever your max is. Or we could do it the other way around. E max equals 1.414 times E effective. So if I know the effective, like I know it's 110 coming out of here, or 120, whatever you want to call it. We'll stick with 120 because I wrote it first. 120, I could multiply that times 1.414, and I'm going to get my peak voltage. Who's got their calculator? Do that real quick. So 169. So really, what is the voltage coming out of the wall? If I look at it on an oscilloscope, its peak is going to be 169 volts. But what's its RMS value? 120. Follow? Okay. All right. Important point here. For all practical applications, the value stated is RMS unless otherwise stated. The value stated is RMS unless otherwise stated. So in other words, I don't go around saying, well, that's a 110 RMS. Well, why you got to throw an RMS? This is 110. This is 120. But if I said it's 165 peak, you go, oh, got it, peak. Because if I said it's just 169, you'd be like, no, it's not. But if I said, no, that's peak, and you go, oh, I know what you're talking about.
When would you need to basically say one or the other, I guess?
Well, especially when you're measuring something on an oscilloscope,
Oh.
because it's not going to give it to you in RMS. It's going to give it to you in the peak, peak to peak. So, all right, that seems like I probably hurt you bad enough for one night.